Uranium, it's rare and it's valuable, and it's a critical mineral that the United States doesn't produce nearly enough of. In fact, we only produce a tiny fraction of our needs. But uranium is a widespread metal. It's a gray metal that doesn't occur as a metal in nature. It occurs combined in minerals. It's thought to be the 51st most common element of the Earth's crust. And that puts it right about in the middle kind of thing. And, you know, it's actually more abundant than a lot of stuff that you're more familiar with, maybe silver and gold and platinum and that kind of stuff. There's more of that. I'm sorry, there's more silver and gold and platinum, and there's more of uranium than there is of those metals and a lot of other elements too. So it's kind of common, but it's not concentrated in a lot of places. It has a lot of different kinds of deposits that occur. We're going to talk about in that with uranium geology. It's commonly associated, not always, but commonly associated with rare earths and sometimes even with gold. So we're going to get into that and talk about the geology of it, but we're talking first about the occurrence of it. It was discovered long ago in the 1700s. A guy discovered it and named it after the newly discovered planet of Uranus in the solar system. And so that's why they called it uranium, because it was unusual. And it's, like I say, fairly common. It occurs in a lot of different kinds of deposits. It's mined both in deposits as a primary metal, where the main mining that they're trying to get is they're trying to get uranium out of the deposit. And it's also mined in a lot of deposits where it's only a byproduct. It may only be a fairly minor byproduct, but it's worthwhile for them to extract it out of the ore. Now, it has some very special uses, and the truth is, when it was first discovered, it was kind of like, oh yeah, you know, there wasn't much use for it. And for a long time, the only real use for it was because some uranium minerals are very colorful. They used it for glazes, for pottery and things. And they're still, to this day, I've seen pictures and I've seen them in person, plates and dishware, you know, that you could buy to put your food on that's glazed with a uranium glaze. And they don't recommend that you put your food on that, but that's what those glazes were originally made for. You can see it's a regular standard plate. It's kind of a red color, but anyway, it was used for that, and really there wasn't any other uses. And then discovered at the turn of the century, close to 125 years ago, Madame Curie in France and her husband, before he passed, discovered that associated with uranium was a small amount of another element they called radium. And so they started mining uranium to extract the radium for it, and it was used to make glow-in-the-dark dials and stuff for clocks and things. Of course, it was way more hazardous than was realized at the time, and the people who worked extracting radium out of the uranium, because radium is a radioactive element in itself, and so they extracted that, and most of them died at a fairly young age because of high exposure to radioactive materials. Anyway, but the uranium that they mined to extract the radium from, they didn't know what to do with it. There was a lot of it, and there was no particular use for it. It wasn't until the 1930s that the late 1930s, that some experiments in Germany, unfortunately, we were lucky on this one, we dodged a bullet. There was a lady who was of Jewish heritage, and a guy chemist they were working on stuff, and the guy chemist, you know, they didn't understand what was happening to the uranium that they were bombarding with other radioactive particles. But the lady got it, but she also escaped because of the persecution of the Jews. And she got to the United States and talked to other scientists, and they figured it out, and they tested. What they were discovering was that small parts of uranium, and we'll talk about this, is subject to what they call fission. And so when you hit a uranium atom, a fissionable uranium atom, with a neutron, it splits in two and releases a whole bunch of energy. Of course, this is the reaction that led to the generation of the atomic bomb. Now, uranium, like I say, it's all radioactive, and the half-life of normal uranium, most uranium, the isotope that makes up the bulk of uranium is uranium-238. And uranium-238 is itself not fissionable. It can't be broken in two easily. And it has a half-life of about 4.5 billion years. And so if you had a pound of uranium and you set it on a table and came back in 4.5 billion years, half of that uranium would be gone. It would be decomposed into other stuff. And if you came back in another 4.5 billion years, there'd only be 1/4 of a pound of uranium left. It would have decomposed into other stuff. Now, there's a whole chain of reactions that uranium decomposes into different things, and those things are actually usually much more radioactive than the uranium-238. One of the products is the radium that I mentioned a minute ago. The final product, which is stable, is an isotope of lead. So uranium decomposes down into lead over a very long time frame. But about 0.7% of natural uranium consists of an isotope called uranium-235. And the difference is both of those uranium forms have 92 protons and 92 electrons. The uranium-238 has a few more neutrons. Uranium-235 has 3 less neutrons, and uranium-235 is the form that splits. That if you hit it with a neutron, it will split, and when it splits in two, it doesn't always split into the exact same elements. It's unstable when it splits and splits into different things, but it also releases a few neutrons, and those neutrons can then interact with other uranium-235 and split and create more neutrons and more and more and more. And so as it splits, it's a chain reaction that keeps on going. That's what happens in an atomic bomb, the explosion of an atomic bomb. In a fraction of a second, one uranium atom splits and another and another and another, and another, and it just goes in a big chain reaction, and pretty soon, boom, the whole thing. So let's talk about what uranium looks like and the critical uses of it and the idea of an atomic bomb. Let me show you some diagrams and pictures.
Here is a disk of uranium metal that shows what it looks like. And you can see that it's just a gray silver metal. It's very dense and heavy, but has a normal look to it as a metal. Here's a model of the uranium atom, and it has 92 protons and 92 electrons, and most uranium atoms have 146 neutrons. Some have 143 neutrons, but that's only about 0.75% have the 143. But those are especially important. Now, it's so large that the forces inside the atom, it can't be fully stable. And even the version with 146 neutrons, that's why it decomposes. It's just so big, it can't be stable. Now, the version with 143 neutrons is called uranium-235 because there's 92 protons and 143 neutrons, and added together, that's 235. So this atom has a special instability in that if it absorbs one neutron, it will break apart in two. It won't just be radioactive. It'll literally split the atom into two fragments that are about 1/3 and 2/3. In this example, it's an atom of krypton and an atom of barium that it splits into. but when it splits, it releases a few more neutrons. And these neutrons can then go to other uranium-235 atoms and split them, and they release extra neutrons, and this splits more and it splits more, and that's how you get this chain reaction that yields a nuclear explosion if it happens too fast. Now, it also releases, when it splits, a huge amount of energy, and shown in this diagram by the big orange splotches. There's a lot of energy released, and that's the energy of an atomic explosion, or if you can control it, a nuclear reaction to generate electricity. In order to be used for a nuclear bomb, the uranium-235 has to be very high purity. Instead of being just 0.7%, which it is naturally, it has to be upwards close to 100% in order to work for a nuclear explosion. But if it's just enriched a little bit to maybe 5%, it can be used to generate fuel or generate heat in a nuclear reactor to generate electricity. And this is a bundle of enriched uranium, enriched a little bit, so that it can be used to generate power and electricity. This is what a fuel bundle looks like.
Next, let's talk about uranium mining. Okay, uranium is mined in all different sorts of ways. It's mined in open pits, it's mined underground, and it's mined in even a kind of a unique way. And it's not only uranium that's mined this way, but some other elements are too, called solution mining, where they basically put down two wells and they will put solution in at one level, and the uranium will be on a horizontal level, and they'll put solution in that dissolves the uranium mineral, and then at the other well they'll suck it out. And so as this material goes through, it gets sucked out, and they extract the uranium from the material that they suck out of the second well. So this material goes down, dissolves the uranium, and gets sucked out and then recovered. And the uranium is produced into a standard material called yellow cake, from which uranium then is extracted. It's a uranium oxide. Like I say, many uranium minerals and uranium chemical compounds are very brightly colored. And so let me talk a little bit more about uranium mining and the ways that works.
Here's a diagram that shows the different types of mining that take place for uranium. On the left is open pit mining. We'll look at that a little more. Then in the middle is underground mining, and we'll look about a little bit at that more. But we've got a shaft or an adit going into underground workings where you would extract the ore. That's done with underground. But then there's this in situ mining or solution mining that I mentioned, and you can see that the material is pumped down, the blue side on the left. It goes across in the ore layer and then is sucked up and processed in the plant. And, let's take a closer look at the open pit and underground. This is an open pit mine, an open pit uranium mine in the Athabasca region of Canada. And you can see it's a very large excavation with, haul trucks that work their way around down into the bottom where they can be loaded with ore. And this is the head frame above a shaft of an underground uranium mine in the Colorado Plateau region of the United States, where a lot of uranium was produced back in the day. However, no matter the method that the uranium is mined by, it's eventually processed into this material called yellow cake. And we produce many millions of pounds. It's the first step in producing uranium metal and enriched uranium products for either nuclear power generation or nuclear weapons.
Now, uranium geology is kind of unusual. A lot of different kinds of elements have only just a few types of deposits that are economic. Now, gold is one of the ones that has a lot of different kinds of deposits that are economic. But, like lithium, it's either brines or pegmatites or some other thing. There's a limited number of different types of deposit. Uranium has a whole bunch of different ones that are widely unusual. And sometimes it's associated, in fact, it's pretty common that it's associated with rare earths. It may be a rare earth deposit that has a little bit of uranium, or a uranium deposit that has a little bit of rare earths. It's very common that the two are associated together. In fact, there's some places like in the United States that they don't capture the rare earths in their deposit. That's a deposit that's mined for heavy sands. They don't recover the minerals that are radioactive because of the difficulty of getting the uranium and the difficulty of handling radioactive materials and the safety and dangers of it. So, sometimes, they're associated. And so when you prospect for uranium, you may also be prospecting for rare earths. And you actually can be prospecting for gold and copper too, which is kind of unusual. But there's actually a spot here in Washoe County, which is the county in western Nevada that I live in. And way up north, there's a deposit that a mining company way back in the 1980s was doing some searching around for a certain type of uranium deposit called a caldera-related uranium deposit. So they were looking around up there and they took some samples. I don't think they ever really found a viable uranium deposit. They might have found a little tiny bit here and there, but not a viable, mineable deposit. But what they did find was a gold deposit. So, searching for uranium may produce gold, and it's possible that you could be searching for gold and then accidentally find uranium. The other thing about rare earths is that there's a deposit in California called Mountain Pass that's been a very productive rare earth deposit. I think it's still producing some rare earths, and it was originally found by a guy who was out looking for uranium with a Geiger counter, and he found some radioactive stuff, and he thought, oh, this is pretty good. And when he went and tested it, he was disappointed because it was a rare earth deposit with only a little bit of radioactive stuff, and most of the radioactive was not uranium but thorium. So there was a little bit of thorium and uranium, and that's what he discovered, but it was really a rare earth deposit. And later, when rare earths became more valuable and more important, the technology was developed that needed rare earths. It turned out that the deposit was super valuable, but initially it was prospecting for uranium. Yeah, in fact, there was a big uranium boom in the late 40s, 1950s, and into maybe even the early 60s, so maybe 15 to 18 years of just everybody was looking for uranium because uranium is, it was considered to be part of the future. That, we had discovered this power of splitting the atom, and, it was set up so that, we have these nuclear reactors that produce electricity, and it was thought that in the future that would be a big source of electricity for worldwide. Well, it hasn't quite worked out that way because the dangers of the daughter products, when you split the atom, you get two other different types of atoms plus some neutrons and some energy, but those other elements are also usually very radioactive and dangerous. So it's not good stuff. It's worth taking a look at the geology. Let me show you a little bit more about the geology of uranium.
Here's the geology of some of the sandstone-related uranium deposits. I have marked on here number 1. This is what's called a roll front. And what you have over on the far left, the pink, is uranium-bearing granitic rocks, but it's real low grade. But as water leaches through, it'll push the uranium through, and you may have adjoining sandstone, and basically a wave of uranium is pushed through, and as it encounters reducing materials in the sandstone, it gets precipitated, and that's marked as number 1. Number 2, the uranium gets precipitated in a layer of lignite coal, and of course the coal is a reducing agent and will capture the uranium. Number 3 is a tabular type of deposit of uranium where you have reducing material in the sandstone. And number 4 is a tectonic type, and it captures it also along fault zones. The roll front type, marked as number 1 on this diagram, is a very common one in the Colorado Plateau of the United States and produced a lot of uranium. Another type is the unconformity type, and this is an example of it. You should have a cross section here where you have sandstone up above, and then you have crystalline basement rocks, and the uranium deposit occurs right on the contact of the two, which is basically an unconformity. And this is Athabasca sandstone. This is in the Athabasca region of Canada, and the ore can be very high grade, and there's quite a lot of uranium mined from these types of deposits in Canada. Another type is the ancient pebble conglomerate, and this is actually a bit of gold ore from the Witwatersrand district in South Africa. And this type of ore does contain small amounts of uranium, and since they're already mining and processing it for its gold, it's worthwhile to extract the uranium that's in there too. And you see, gold and uranium can be associated.
I also want to talk about uranium minerals so that you would recognize them when you see them in the field. Some of them are pretty nondescript. Others of them are very brightly colored. And so, some of them, like I say, they almost glow in the dark. And others of them, don't show much. They're just dark colored. All of them, or many of them, light up on a UV light. So that's another way of prospecting. So let's talk about uranium minerals, and I'll show you some pictures.
This is pitchblende. It's also called uranite, and it's really the most important uranium ore, and also the most common in deposits that are rich. Here's another example of pitchblende. This is from Canada. It's the most common mineral in the unconformity deposits that make up the really rich Athabasca Basin deposits of uranium. Now, it looks black and kind of nondescript, and so it's really hard to tell these kinds of minerals just by looking at them. The silver ores can look black and sooty like this, and so can manganese ores. And uranium is, of course, much different. It will set off a Geiger counter. This is coffinite, another dark-colored uranium silicate mineral. It's found in various deposits, and it's often associated with pitchblende. This brown mineral is brannerite, a uranium titanium oxide mineral, and it's an important source of uranium and radium. There's a related mineral called davidite, which is also a uranium titanate. Now, this is the most important mineral at the Olympic Dam deposit in Australia, and Olympic Dam is actually the world's largest uranium deposit. It's mined primarily actually for gold and copper, but it has this secondary uranium, which, since they're already mining it for the gold and copper, it's well worth extracting the uranium at the same time. This is samarxite, which is part of a group of uranium, niobium, and rare earth oxide mixtures. And this mineral, like I say, it has a number of products. Both uranium and niobium and the rare earths are quite valuable. And so deposits like this are well sought after. Now, the dark minerals we just looked at are the primary uranium minerals. These are the ones that form by geologic processes in the ground. But when you have a weathering with the water and oxygen from the air, you can turn these primary uranium minerals into secondary uranium minerals. And so now we'll take a look at the bright colored secondary minerals. And first we're going to take a look here at carnotite. This is a yellow uranium potassium vanadate. Then it's the most common secondary uranium mineral. It's mined extensively in the Colorado Plateau, or at least it was mined extensively in the Colorado Plateau area of the United States, including Utah and Colorado and some other states. This mineral is autunite, a widespread and brightly colored secondary uranium phosphate mineral. I actually mined a little bit of this in the deserts of Southern California long ago. This green mineral is tobernite, which is another common and brightly colored secondary uranium mineral that also has copper in the mineral. This bright yellow mineral is gummite, which is another oxidized uranium mineral and is sometimes associated as a weathering product of pitchblende. And this bright yellow mineral is uranophane, which is a uranium silicate mineral, also another secondary uranium product. Now, all uranium minerals, whether the dark primary minerals that I've shown you or the more colorful oxidized minerals, the secondary uranium minerals, they're all processed into this product, which is called yellow cake. And prices for uranium right now are actually above average. They are currently about $70 per pound of uranium in the yellow cake. And the production rate of uranium that we're currently doing does not meet demand. The need for more uranium for power plants is expanding and growing. And even though in the United States there's a strong voice against the use of nuclear power plants, around the world, in Europe, China, India, and elsewhere, there are many countries moving to increase their nuclear power production capacity and wanting more uranium to make that happen. And so the outlook for uranium prices in the long run is really actually pretty good, especially as we need more and more electricity for AI applications as well as for electric automobiles.
So now let's talk about uranium prospecting. I mentioned that a black light is super valuable, but one of the things that you can get is a radioactivity meter. And I've got here, I was sent this radioactive tester by a company, and I'm going to do a little review of it as part of this video. But this is the kind of thing you could take out in the field and do some testing with and find uranium minerals. So let me show you this. Let me unbox this and get you this out and show you about testing for radioactivity. It's also, if you have any concerns about stuff, if you're worried about radioactivity, this thing will help you test it and recognize that. So let's take a look. So because I'm doing a video on uranium and uranium prospecting, I had a company send me a Geiger counter. And if you want to go prospecting for uranium or any other radioactive material, you need a Geiger counter. Now, in the old days, Geiger counters used to be big and bulky and heavy and consume a lot of battery power, of which it was hard to supply them. But I got this little device. It's not very big. It's just a few inches by a couple inches and about maybe a little more than a half inch thick. And I'm real excited about it. It was sent to me for free, but if I'd have known this was available, I'd have bought one for myself. They used to be a few $100s. This thing is currently on Amazon for $51, and in the description below, I'm going to put a code that you can put in for a discount on the thing. And I went around and tested it in a few things. Something that most of us are familiar with, the element potassium. Potassium is required for our bodies. All of us have potassium in us. If we didn't, we'd be dead. But a small amount of potassium, about 1/100% is actually slightly radioactive. And so I took my bowl full of a salt substitute that I used to keep my sodium down and tested it, and sure enough, it showed a little tiny bit of radioactivity above background. But if you ever have any questions, and ever want to, find out about something, whether or not it's radioactive, this thing is easy and quick. And you use it like it is a Geiger counter. It's easy to turn on. It has a little color screen. On the front here, I don't know if you'll be able to see this, but there's a little LED light that detects when it sees something, when it sees a radioactive decay. It will not do alpha particles. Alpha particles are easily stopped. A piece of paper will stop an alpha particle. But it will see beta particles and gamma rays and X-rays. And so it's good for testing for X-rays. If you're in an environment where, they're doing X-rays, this thing will test and tell you if you're being exposed. Now, I happen to have a 1 ounce bottle of thorium nitrate. And don't ask me why I have an ounce of thorium nitrate. I'm not going to answer that question. But I have it, and it's an old bottle. That thing was probably bottled at a factory around the time I was born, okay? So it's been sitting around. And radioactive elements, especially ones like thorium and uranium, they decay through a process. And they'll basically give off an alpha or a beta or some other particle and then decay to something else. And then that will give off radioactivity and decay to something else and decay to something else. And eventually, both uranium and thorium become lead. And the end product that's not radioactive is lead. So I have this little device, and I have my 1 ounce bottle of thorium that's old, and because it's old, it's had a chance to decay, and so it has a lot of those daughter products, and the daughter products are radium and radon and polonium and other elements that are definitely radioactive. And so I'm going to give you a little demonstration. Right now it's reading 0.07 as a background number. But I'm going to take my little bottle and put it up here to the back, to the sensitive area. And I don't know if you can see it, but this little LED that flashes when it sees things, now, one of the things about Geiger counters is they take a while to read. They are counting radioactive decays. And so it takes a while to go up to see what it's in. And now it's done with a cycle where it was reading stuff and it's back to background level. But because it counts over a period of 10 or 15 or 20 seconds, it takes 10 or 15 or 20 seconds to take a full reading. It takes 10 or 15 seconds when you remove the source of radioactivity to go back and show background levels. And one of the things about radioactivity is distance makes a difference. Okay, when I held this to the back, but now I'm going to hold it, about a foot away. And it's just not showing that much. The distance makes all the difference in the world. It is showing some, and it's going to go up, but it won't be beeping red like it did. It's showing a little bit above background. But see, a foot of distance is greatly reducing the amount of radioactivity. And if I bring it back up again, it has all kinds of things that it's seeing. And pretty quick it will be telling me that I'm being overexposed. Now, Chris, you're going to say to me, Chris, hey, you're exposing yourself. You're touching that bottle. You're exposing it. And it's true. If I held that bottle all the time and, for hours and days, then yes, it would be a radioactive hazard. But for holding it for 20 or 30 seconds or a minute or two, it doesn't add up to. But this is a handy device to have. I highly recommend it. Like I say, you can get it on Amazon right now for $51, and I'm going to put a discount code that you can get even more off in the description below this video. So I highly recommend this thing. I'm excited about it. I'm going to get out and test it and fiddle around with it. I've never had a Geiger counter before, and I'm glad that I can have one. Now, most of my videos are about prospecting for gold and prospecting as a whole, whether it's for radioactive stuff or gold or whatever. It's a skill, and the more you know, the more likely your success. And I published a book on prospecting mostly for gold, but it has information about silver and platinum, diamonds and stuff in it. And my book is called Fistful of Gold, and I've also partnered with an outfit called High Plains Prospectors. And I'm going to tell you a little bit more about my book and about High Plains right now. This is my book, Fistful of Gold. It's an encyclopedia of everything you need to know to go out and find gold for yourself. It distills down my 45 years of experience out in the field prospecting, as well as my degree in mine engineering. It's, like I say, an encyclopedia. There's a lot to it. It's over 250,000 words long, hundreds of pages with hundreds of illustrations, teaching you what you need to know about geology, about mining districts, about techniques of finding gold. It covers metal detectors, sluicing, panning, dry washing, high bankers, you name it, it's covered in there. It talks some about platinum and diamonds, but it's mostly about gold because gold is more widespread. It is not so much a book about where to find gold, but a book about how to find gold. Because even if you have a location where gold was mined in the past and you go out there, well, where should you look to be successful in your prospecting, to find the gold that's there? This is the book that's going to tell you that information. I spent most of 10 years writing this book, so I thought a long time about it. It's got, like I say, lots of information and lots of illustrations, and I've had results from people who bought it. It's available on Amazon, but I recommend buying it through High Plains Prospectors, and I'll put a link in the description for buying this book through them. They have a better price than Amazon, and I have a special deal that I'll tell you a little bit more about, where you can get a 5% discount from the price even with that. On Amazon, the book rates a 4.7 out of 5, which means that of all the people that have bought it, they've been really highly satisfied, and I think you, if you buy my book, will be just as highly satisfied as well. Now let's talk a little bit more about High Plains Prospectors. They're a prospecting shop, a mail order prospecting shop that I've partnered with. The deal is that I can get you a 5% discount, a coupon code, and I'm going to put the code to that right here. It's just Chris Ralph, all caps with no space between Chris and Ralph. You put that in there as a discount code and you'll get 5% off their already really good prices. I think it's a great deal where you win by getting a discount, I get a little percentage of that, and they get new business. So if you need prospecting supplies, High Plains is really the way to go. And I'll put information, like I say, in the description more about how you can work with them, because I'm working with them. They really are great guys, a great company. For even more information, I also have a website, and I'm going to show you my webpage and talk a little bit more about that right now.
This is my webpage. It's located at nevadaoutbackgems.com. You can Google it, or I have a link down in the description below. But there's lots of information here, miscellaneous stuff, pictures, some historic information as well, stories. It's got a lot of great fun stuff. You'll probably be interested in it.
Now, on all of my YouTube videos, I encourage you guys to ask questions. If you have thoughts, comments, suggestions for things that I ought to look at in my videos, things that you want to find out more about, and I answer 100% of my questions. There's not very many YouTubers out there that answer 100% of their questions. I'm one of the few. And so I will do my best to answer what you have. I mean, I only can write so much. Sometimes the answer is something where I'm going to recommend that you buy the book and read about it. I also ask that you subscribe to my channel, click the bell notification so that every time I come out with a new video, you'll be able to watch it. And like I say, I cover a huge amount of topics. I also have 250 videos that I've already done. And so you can go back through my catalog of videos on YouTube. I'm sure there'll be many videos there that you'll want to take a look at, especially if you have any interest in gold or platinum, diamonds, gemstones, geology, and that sort of stuff. My YouTube site is going to be right up your alley. So I'll see you again real soon. We'll be out in the field and back in the office at the whiteboard, and whether we're looking at gold or platinum, diamonds, gemstones, or other interesting geology, it's going to be fun. You're going to enjoy it, and we'll see you again real soon.